Hi, for this video, we will talk about electric potential energy. Potential energy can be generally described as the energy stored in an object or energy stored in a particle due to its position. Electric potential energy is the energy that is needed to move a charge against an electric field. It is also defined as the work required to assemble a system of charges by bringing them closer together. Well, as in the system from an infinite distance. Alternatively, the electric potential energy of any given charge or a system of charges is termed as the total work done by an external agent in bringing the charge of the system of charges from infinity to its present configuration without undergoing any acceleration. When you look into your previous lesson and when you look into your knowledge about the relationship between work and energy, this is also applicable in the concept of electric potential energy. Now recall that for a conservative force F acting along the x direction, force can be calculated as the negative change in potential energy divided by its change in position. Or, if we transpose the change of x or change in position, force times change of x is equal to the negative change in potential energy. Now, your force times change in position is also equal to work. Thus, when a particle moves from 2 points, let's say point A and B, so the work done from point A to B is equal to the negative change in potential energy or electric potential energy in this case. And change in electric potential energy is the difference between your potential energies from point B to point and point A. Then we can distribute this negative sign, and then that will give us work from point A to point B is equal to the difference between UA and UB, or UA minus UB, or the potential energy in point A minus the potential energy in point B. It's also important to take note that if the test charge moves in the direction of the electric field, its potential energy decreases. On the other hand, if it moves against the direction of the electric field, the potential energy increases. So it somehow works like gravitational potential energy. Remember, when you have an object and you move that object closer to the ground, which is in the same direction as your gravitational force, then you will have a decrease in gravitational potential energy. But if you go against the gravitational force and you move an object that is going towards a higher position relative to the ground, then that object will have an increase in gravitational potential energy. So this is also the same for electric potential energy. If your test charge moves along with the electric field towards the same direction, then your electric potential energy will decrease. But if it goes against the electric field, then that will give you an increase in electric potential energy. So let's have here an example. A point charge of 2 nanocoulombs with a mass of 4 grams is moved from a position of 1 meter to 1.5 meters in an electric field of 6 newtons per coulomb with the same direction as the motion of the charge. A. How much work is done on the charge by the electric force? B. What is the change in position? What is the change in potential energy of the charge? And C, assuming that the charge started from rest, what will be its speed if it's now moved to 1.5 meters with respect to changes in kinetic energy? So our given values, you have your charge, which is 2 nanocoulombs, and if you convert that into coulombs, that's 2 times 10 raised to negative 9 coulombs. And then you have your mass, which is 4 grams, and 4 grams is equal to 4 times 10 raised to negative 3 kilograms. And then we have your change in position, and your change in position will be the difference from 1.5 to 1 meter. So that's 1.5 meters minus 1.0 meters, and that will give you 0.5 meters as change in position. And of course, we have our value for electric field, which is 6 newtons per coulomb. So for letter A, we need to solve for the work done. So how much is the work done? Remember that work is equal to force times change in position, or force times change in x. And force in terms of electric field is equal to charge times electric field. So if force is equal to charge times electric field, then work will be equal to charge times electric field times change in x. So we substitute our values for that. Our charge is equal to 2 times 10 raised to negative 9 coulombs times electric field, which is, how much is our electric field? That's 6 newtons per coulomb, times our change in position is 0.5 meters. So we're left with Newton meter as our unit, which is also expressed in joule. So that's 2 times 10 raised to negative 9 times 6 times 0.5. So that gives us work, which is equal to 6 times 10 raised to 9 joules. So this is our value for the work. So the work that is done by moving the point charge 2 nanocoulombs from 1 meter to 1.5 meters is 6 times 10 raised to negative 9. Oops, raised to negative 9. Let's rewrite that one. Raised to negative 9 joules. Next, let's proceed to question B. So for question B, what is the change in potential energy of the charge? Now for the change in potential energy, work is equal to the negative change in potential energy. So to solve for just potential energy, then we can transpose this negative sign to the other side. Or in other words, we can multiply both sides by negative, and then this becomes positive, and then this becomes negative. So your change in electric potential energy is equal to negative work, and work is equal to 6 times 10 raised to negative 9 joules. So your change in potential energy is negative 6 times 10 raised to negative 9 joules. Now for C, assuming that the charge started from rest, what is its speed at 1.5 meters? So our initial velocity will be 0 since it started from rest, and we are to solve for its final velocity. Now, how do we solve for that? We know that your work is equal to the total change in kinetic energy, according to the law of conservation of kinetic energy. With the law of conservation of energy, the total change in kinetic energy will equal to your total work done. And your change in kinetic energy is Ke final minus Ke initial, which will give you Ke final is 1/2 mvf squared minus 1/2 mvi squared, or mv0. And our mv0 is 0. And any number multiplied by 0 will give us 0. Therefore, work is equal to 1/2 mvf squared. But we are just to solve for vf, so we need to derive an equation for this value, and that will give us Vf is equal to the square root of 2 work divided by its mass. So Vf is equal to the square root of 2 times the work done is 6 times 10 raised to negative 9 joules over the mass is 4 times 10 raised to negative 3 kilograms. So if we put that in our calculators, that is the square root of 2 times 6 raised to negative 9 divided by 4 times 10 raised to negative 3. So that will give us your value for the final velocity at 1.73 times 10 raised to negative 3 meters per second. So that's our final velocity. So that's it for our lesson on electric potential energy. Thank you very much for listening and see you the next time.